Let's begin. I don't remember what section we're in, but there are.
Some movies will appear.
Yeah, I meant the number. So, there are three fundamental PDEs. Well, there are more, but these are the big three. These are fundamental in describing our world. They describe a lot of important things in classical physics and differential equations, which tells you all about physics. One is called wave equation, not the one from quantum, the classical physics one. The one from quantum, there's a Schrodinger wave equation, not that one, the other one, the other wave equation. So there's something called the wave equation. These are guys, yes.
What's a PDE?
Partial differential equation. A PDE stands for partial differential equation. Like a differential equation, but they're partial derivatives instead of just ordinary derivatives, meaning that we're going to be looking at a situation where there's more than one independent variable. Wave equation is a very important type. These are guys that look like this, where you might have a constant in front of here. So that is you have a function of x and t. T usually represents time. This is the second partial derivative of some function with respect to t, and it's set equal to, it's proportional to the second partial derivative with respect to x. This describes the propagation of waves. It could be water waves, could be sound waves, could be a lot of things. It describes waves in a general fundamental way, where the wave that you're looking at would kind of change what this constant is being, the constant that you would choose here. Another one is called Laplace's equation. So this one looks more like, almost like a Laplacian, right? So uxx equals uyy. Again, sometimes a constant can be over here. That one kind of governs, well, a lot of things, but maybe the deformation of bodies would be one of them. You take a steel plate, maybe like a flat square steel plate, and you bend one of the edges so that it looks like a parabola, and you kind of measure the gradient along that surface, how the gradient changes over time as you slope across the surface. That kind of equation is going to pop up. It's called Laplace's equation. Laplace was studying this equation when he was studying gravitation, which some people think of as a bending of space-time. Then there is something called the heat equation, or the diffusion equation. This describes how things diffuse over time. Most commonly, it will be spoken about how heat would diffuse through an object over time. The guy who was studying this situation, which this one looks like ut, uxx, and you might have a constant in front of here, which we'll talk about. The guy who was studying this was actually Fourier. And he was studying heat conduction, and he came up with the heat equation. These three are fundamental. If you take any PD course worth its salt, it's going to talk about these three partial differential equations, among others, because not only are they important in physics, but they're just important as general examples. They're canonical examples for a lot of mathematical situations that we'll tend to find ourselves in. We're not going to talk about all of them. We're going to talk about one of them. We're going to talk about the heat equation. That is the topic of this lecture. So we're going to talk about the heat equation, and while it's not hard to actually derive it, it'll take you 10 minutes or so. I don't know, at least for me, especially if you're not big into physics, you can't really get a lot of intuition from the derivation. So I'm kind of going to talk about how you come up with this equation in a more intuitive sense, not necessarily in a mathematically rigorous sense, but just like why you can see that it might be true. Maybe sort of just start out with some basic assumptions, see how that equation was developed, and then you could proceed like a scientist and just check it empirically, whether or not it works under various conditions, and you can get more precise values of this constant based on the materials. So I just want to talk about a more intuitive way of coming up with the heat equation, which I don't know, a while ago I saw another YouTube video that kind of explained it this way, and I really liked how it explained it. So whenever I'm in a situation where I forgot, like, what does the heat equation again say again? Like, this is how I remind myself. I don't actually go through and derive it from scratch. So I thought I would show you that. So here is the situation.
What video is it?
I'll actually link it. Chris, remind me to link the videos. And remind me to link all the Fourier videos, or you're slacking. Okay, so the situation. Let's say we have a metal rod. Right? Let's say it has length L. So a thin metal rod is heated, and we want to measure the temperature distribution at any time and any quantity. So, in other words, i.e., how heat diffuses through the rod. Now, what you're going to know with PDEs is the dimensions will blow up very quickly. So we're going to consider a very simple situation. So let's look at the assumptions that we're making here, just so that things don't get out of hand too much. The rod is infinitesimally thin. So almost to the point where you can almost consider it as a one-dimensional object. That's going to be important. Okay. So 2, at cross sections. We have constant temperature. Which means if I were to slice this guy, right, and I take out this disc, everywhere along this disc on this vertical plane, I will say has the same temperature. If I take another slice somewhere else, it might have a different temperature, but along that slice, every point along that slice will have the same temperature. The wire is so thin that we can make this assumption. 2, very physicist kind of assumption, the rod is perfectly insulated. Of course, can't actually happen, right, any more than cows are frictionless spheres, but we're going to sort of assume that heat is not being lost through the sides of the rod. It's perfectly insulated. There's insulation around it, so there's no heat loss from the sides. There's no heat loss from the ends. Heat distribution is completely moving left and right throughout the rod. Now, under those conditions, how can we actually measure how the temperature will be diffusing throughout this rod? Well, we are simply going to define a function that is going to do the measuring for us. So, what we're going to do set a function that we call u of 2 variables, u of xt. To be the temperature of the rod at horizontal position x and time t. Right? So at any given time, I can find some x position along this rod. So let's say here is our rod again. I'm considering this location, say x equals 0, running along the length this location is x equals L, so the rod has length big L. And if you pick a location, tell me an x value along this length, and tell me the time, I am going to try to figure out a function that's going to measure the temperature along that cross section. So at any given time and location, I can tell you the temperature. Right? We want to actually find a function that does that. Now, the reason why differential equation is so important is that a lot of times finding rates of change of something is easier than finding the thing itself. And ultimately, when we talk about the rates of change, it's going to help us to talk about the thing itself by solving the equations in terms of rates of change. So let's actually see what would happen here. So let's say, as an example, here's a candle, and I am going to be light a flame here. Well, it's almost the last class. I have all this colored chalk. So there's a flame right there, right? And it's heating up this rod. So what you can imagine is the point where the flame is super hot, right? But as it diffuses, it gets cooler as you move away from the point of the heat distribution. Right? So right here is hotter, and then it's slowly getting cooler as you move away, right? Now, let's say I wanted to actually plot the temperature change over this period, right? So let's say here, I'm going to graph U versus X. What would this graph actually look like? Well, at this position, it's going to have a hill, right? And then it's going to slowly slope down, right? So it's going to look like that. In the middle, there's a very high temperature, and the more you move away from the middle, the temperature keeps tapering off in some regular fashion here, because it's a very ideal situation. Now, there are many laws that actually say this. Fourier actually came up with his own law here for heat distribution, but it kind of goes by the law that you guys would all actually know. How does heat actually travel? How does it conduct? Is there a direction to it?
Hot to cold.
Right, you go from hotter, heat moves to colder places, right? So what's going to happen is when this is hot, the heat is going to be distributing that way. It's going to move out that way. So what you're going to realize is that in the middle, right, what is going to happen to the temperature at this point? It's going to start getting lower because it's going to start redistributing heat away from itself. And so the heat right in the middle here, it's going to start getting colder. The temperature is actually going to drop. What is going to happen here?
Rise higher.
They're going to rise higher because if you look over here, there's a point close to him that's hotter than him. He's going to transfer heat to this point, and he's going to rise. He's going to get hotter. Same thing here. Now you can kind of keep doing this motion here, and you realize that as you get closer to the middle, the temperatures are rising, but they're rising a little less and less over time. And here, the temperature is falling, but it's falling a little less and less over time, to the point where there comes a point here where there's almost zero temperature difference. But you kind of have these two things coming together. Now, here's something that you can notice from what's going on here, right? So here's ready for the stroke of genius. One thing you can know about these arrows, here notice that you have a positive temperature change wherever you see a red arrow. And you would also notice that in this part of the graph, you are concave up.
Oh God, California.
Over here, right, positive temperature change, how is it shaped? Concave up. Here, where you have negative temperature change, how will the graph actually behave there? It'll be concave down. That's shaped like a frown. And the crucial observation here is to notice that the temperature change and the concavity will always have the same sign. same sign. Whenever it's concave up, the second derivative is positive, the temperature change is positive. Whenever it's concave down, the second derivative is negative, the temperature change is negative. What do you notice here is that the temperature change has same sign as the concavity. At least of the wave profile. Now we can talk about, and these errors kind of represent what they're doing over time, so I can even add over here. Temperature change over time is going to be giving us the same sign as the concavity, right? When the temperature is falling, I'm getting concave down, and the temperature is rising, I'm getting concave up. I kind of have a graph that looks like that. Now, here's another simple assumption, just to make the situation a little bit ideal so we can actually get somewhere. And you kind of come back afterwards and then kind of verify that this has to be true and what the specifics have to be. So here we make another assumption. Say it is proportional. Right? So it might not give you the exact magnitude as the concavity, but we can assume that it's kind of proportional to the concavity. In other words, the rate of change of temperature over time, which, how can we write that with derivatives? Of course, u sub t, right? We will think of this as some constant factor times the concavity of that graph with respect to x. What does that mean? The second derivative. So I can describe the temperature change in terms of concavity. In fact, it's going to be proportional to the concavity. That's the assumption. What should the sign of this guy be? Well, u and t and uxx always have the same sign. Right? So if this guy's positive, that guy's positive. This guy's negative, that guy's negative. What does that mean for the sign of this guy?
Changes depending on position.
It has to be positive in all scenarios. So this means that this constant proportionality must be positive. So whatever that constant is, I know it has to be a positive number. So what we normally do, when we want to emphasize that something's positive, we write it as a square. So what we're going to do is we're going to set gamma equals alpha squared, which is typically what's used. And we obtain this equation, ut equals alpha squared uxx. This is what's called the heat rate. Now, you could go back after this. You made a lot of ideal assumptions. So you might actually go back and investigate whether or not this relationship is true. So you can take a bunch of different materials and kind of measure the temperature change and concavity of the heat profile over time and really kind of work it out. And it turns out that this thing actually ends up being a pretty good model of heat diffusion. And in fact, we could find by applying all these sophisticated laws, like laws of conservation of energy and Fourier's law of heat conduction and all that stuff, we could find that our alpha squared, we actually even could calculate it. It's K over rho S, where your K is the thermal conductivity constant. A measure of how good the material conducts heat. Rho is the density of the material.
Would it be linear density in this case, since it's supposed to be infinitesimally?
Yes, we would consider it linear density. There is a there is a case where we consider higher dimensions, but that will just be actually adding more terms, actually. And the right side would sort of look like a Laplacian. You'd sort of see like UXX, UYY, UZZ, UWW, and it kind of goes off. So the more dimensions we add, the situation actually gets quite a bit more
The
complicated.
heat will distribute differently.
Because you're thinking of how it distributes in the x direction, how it distributes the y direction, and you have this same argument for all directions, and then we say, oh, the total heat distribution is just the sum of all these, and we just add them together, right? But we're doing one dimension, that is hard enough for an ODE course. S here is your specific heat, which tells you how much energy you need to add to change a unit volume by a unit temperature unit. So that's specific heat. Our alpha squared here is called the thermal diffusivity constant. So you can actually measure this in a lab and kind of figure out that these are what all these things would be. And there are even nicer ways to actually derive these, but I think this idea of just seeing the picture and realize, oh, the concavity is always the same as the temperature change. You get this equation it just kind of makes sense, and then you kind of verify it after the fact. So that's a heat equation. Yeah.
Question. Say if the rod is metal and like we're adding heat to it, will it stretch? Do we take that into consideration?
No. So we wouldn't take that into consideration. A lot of times when they were deriving this, they would think of it as it's infinitely long or whatever, right? But for this specifically, because we want to actually solve a differential equation, we throw in these initial conditions. So we put in a length that we want and all that good stuff. But to actually develop this in general, assume it goes infinitely long. It's an ideal situation. You're not deforming anything. You're putting in just enough heat to actually heat it up and watch the temperature distribute, but it doesn't actually destroy the material, and you lose the linearity of everything. So we kind of have this situation. Now,
Professor, for
Yes.
gamma, why don't we just put an absolute value instead of squaring it? Since gamma is positive, why not put an absolute value? Why do we make another value?
no real reason. I mean,
Makes it nice.
it looks nicer in formulas later on, like if I'm going to take square roots and stuff like that, which you might have to do, and we'll see later on whether we have to do that. Also, absolute value, you usually have to think of those in terms of piecewise functions, and that's just an extra complication for no reason. We impose the following conditions. We are going to assume that, like I said, the rod is insulated, so at the ends there's no temperature loss. In fact, at the ends we can somehow make sure that the temperature is going to be 0. So the first condition is at position x equals 0 and at position x equals L, the temperature change, the current measure of temperature is going to be 0. And this will work for all t greater than 0. Furthermore, we are going to assume that it is possible for us to know the initial temperature distribution. We're also going to assume that at time equals 0, I can tell you what the current temperature at position x is. And let's say it's given by some function of x. So I have some function of x that will tell me in the beginning what is the initial temperature distribution. So you tell me a point x, I can tell you what is the temperature at that point in the beginning, right? It's just that over time I'm not sure what's happening, but in the beginning I kind of know. So if I'm the one lighting the candle, I can measure how hot the flame is, and I know, okay, at the center of the rod it's this temperature. In the beginning, as you move out from it, the temperature distribution is 0. So my function f now is just a piecewise function. It's going to be 0 everywhere else except for a certain region. So we just pretend that we can actually do this, and this would work for all x between 0 and L. I can actually, we're making these assumptions, okay? So now, when you put these together, you get something that is like, kind of like a differential equation with initial condition, but we have to give it a different name to show you that it's much more badass. You know, kind of like how all the way up to Calc 3, perpendicular, you get to Calc 3, orthogonal, man. Like this is perpendicular in infinitely many directions, dude. Like you can be perpendicular in 2 directions. Now, infinitely many, like, perpendicular, all the way around, orthogonal, right? You come up with a new name for it. So, we're not going to call this an initial value problem. Put these together, we get a boundary value problem. The title of the book is Elementary Differential Equations and Boundary Value Problems. Like, this is such an important application that it's in the title, for crying out loud. So this is the kind of equation that is a part of the title of the textbook. It's called a boundary value problem. Because here, it's more than just knowing an initial condition. It's kind of like you knowing the situation around all the edges all at once. I mean, here, yes, there are only 2 edges, but this can go bigger than that. Like, you would be able to define a function that tells you what's happening at an infinite number of points at any given time, given by some other function, right? So it's not like, oh, I know it at this point and that point. No, I know it throughout the entire rod. I know what's going on at infinitely many points. For all points x 0 through L, I can describe it, right? So it's called a boundary value problem. And so you will see in your tests, it will kind of look like this. They'll put like a little squiggly bracket here, and they will tell you the equation that you're looking at. And then they'll tell you, okay, at the ends, at time equal 0, when x equals 0, and when x equals L, the temperature change is 0 for all t greater than 0. This is referred to as the initial conditions line. And u of x0 equals f of x for all x between 0 and L. This is called the boundary conditions line. But you would be given a problem like that. So when it comes to PDEs, there are usually 2 lists of things you'll need because the PDE will work in higher dimensions. You kind of will know what's going on at some endpoints, but also just at the boundary, like throughout some kind of way to know what's going on at infinitely many points all at once. That's called the boundary condition, and you put these all together, you get a boundary value problem.
What is IC?
Initial condition, and BC is boundary condition. Which those 2 phrases don't make too much sense here because we're considering a one-dimensional thing. But as you go beyond this, you'll realize why these things are named that way. Okay, so now, that's the heat equation. Let's solve it. How do you solve the heat equation? Okay, so where do you even start?
Put some numbers.
Check.
Well, do we have a line for L?
Let's solve this. We'll start where we always start. With a guess.
Sure.
Assume. Sure, exactly. That's all. Sure, whatever, man. It's cool. It's cool.
Like, you know what's funny?
Okay.
It's funny that after all these assumptions, we're sitting here learning this, you know? Like, there's so many
Yeah,
assumptions.
and it works. Like, that's the crazy part.
Well, then nature-
Okay. We are going to pretend that u of xt can be written in this form.
How?
I would be able to separate all the x variables and the t variables into 2 nice factors.
Wow.
It's always going to be separable. That's my assumption. Like, it's always separable.
Okay.
That's the assumption. I would always be able to separate the x's and t's. And that worked. Like, let's actually see how this plays out. Okay. So, I assume that a solution looks like that. What does that mean for u sub t? What would that look like? Xt prime, right? What would u xx look like? double prime t. So this means if you plug it in, this would mean x t prime is equal to some alpha squared times x double prime t.
Oh, I see it now.
Now, we're going to separate the variables because we assumed it was separable. Okay, so I'm going to put all the x's on one side and all the t's on the other side. Okay, so let's move the x is over there because the double prime is over there. So over here, we would have like alpha squared x double prime is over here. We have that. And I think just to make things a little bit easier, let's actually put the constant over here. Doesn't really matter, but it's just for something else to pop out to you. Now, here is what we know. So, this function is equal to that function. But they're measured in independent variables. It turns out the only way for that to happen is that they must be equal to a constant. Why? Why must they be a constant? Well, let's pretend that one of them was not constant, right? This is a function of x, but that one is just a constant. Well, that would only work for certain x values, right? I'd be able to solve for it in theory. Okay, if both of them are not constant, so over here I have some functions of x, over here I have some functions of t, well that means I have a relationship between x and t, so they're not actually independent. Therefore, they have to be constants, because in any other case, they would be dependent. I'd be able to find a formula that relates the two of them, which means I can affect x by changing t, or I can affect t by changing x, and we of course don't want that. We want time to be independent of everything. You can't have time being affected by the x position. And so, it turns out, once we separate these, we get that these must be a constant. Now, I'm going to call this constant minus lambda. Okay, let's see. And don't worry, because if that's supposed to be positive, I can just make the lambda negative or whatever. But what does that mean? Well, it means each side is equal to that. So this would mean that my x double prime over x is equal to minus lambda, and my 1 over alpha squared t prime over t is equal to minus lambda. Now, cause equation 1, cause equation 2, let's deal with equation 1. I can rewrite this equation. I can multiply both sides by x, and then I can have that.
Hey. That's
You remember that, right? That's the Sturm-Liouville problem that we considered last class, at the end of last class when we solved it. In fact, I know the initial conditions. When x equals 0, temperature is 0. When x equals L, temperature is 0. So I have an ordinary differential equation, which is second order, constant coefficients, and I know the initial values at 2 location points, and they're both 0. We already solved that. We solved that at the end of last class. What was the solution? X has to be sine of n pi x over L, right? And then our lambda has to be what? N squared pi squared over L squared. Now, what I'm going to do is I'm going to take that lambda and plug it in here. Because it's the same lambda. They're both the same constant. So now in 2, I'm going to have 1 over alpha squared t prime over t equals minus lambda, but my lambda is n squared pi squared over L squared. Which means now I would have my t prime is equal to n squared pi squared alpha squared big T over L squared. That's a first order differential equation with constant coefficients. In fact, that is separable. I could divide through by the t, integrate both sides, I would get an exponential.
Isn't that negative?
It is indeed negative. So this means, that's just the first order, so this means our t has to be some constant times e to the minus n squared pi squared alpha squared t, little t, over L squared. Which means my u of xt, I know what that formula is now. That's just big X times big T. My big X is a sign, my big T is this, so I can just multiply them. So we have that, is what our solution has to look like. Now, another crucial observation. We actually have a solution for every n, right? This guy's going to have the right period no matter what I plug in for n. And it goes 0, 1, 2, 3, 4. Also negative, but let's just keep everything positive. We'll cycle through all things anyway. Right, because if I make n negative, I can just factor out the negative because sign is odd, and it would just look like the original term anyway. So it's actually will work for just the positives, which means we have solutions with u of xt equals c1, xt plus c2, xt plus c3, xt, etc., right? Where here's where I plug in, say, n equals 1 or 0 or whatever. Let's start. N equals 1 or 2 or 3, and I can get a copy of that every single time. So, and of course, we know from the superposition principle, once I find one individual solution, then the sum of that with another solution gives us a solution, then the sum of that with another solution gives us a solution. Notice that I can write this as a series. Where the coefficient is going to change based on which n value I'm picking. And it turns out that a series will actually solve the heat equation. A series solution solves the heat equation. Now, a series is no good unless we can know what the coefficients are. You give me a formula for a series, okay, great, but what are the coefficients? Now you might recall, we didn't use all the initial conditions. There's one that we didn't use yet. The fact that we know the initial temperature distribution. Use the fact that I know that at time 0, position x, there's a function that gives me the initial temperature distribution. So what I'm going to do is I'm actually going to plug that in. U of x0, plug in 0 for a little t, what's that going to give us? E to the 0, which is 1. What do you notice?
Oh, it's thing again.
That's a Fourier sine series.
Yeah. So we can use Fourier series?
So we can use the Fourier series formula to find the coefficient. That's a Fourier sine series. Gasp!
we define, is C and same as C naught, and A naught, which means Fourier?
Yes.
Now what that means is that I know exactly how to find these coefficients.
Yeah, A naught is,
So we started out with some simple assumptions that actually turn out to work. And what do you know? We follow these assumptions to their logical conclusion. Turns out a Fourier sine series solves the heat equation.
I have a question.
Yes.
The reason you can go from 0 to L is because we're also assuming the f of x is also odd, right? Because otherwise if it's,
No, the f of x doesn't even matter. It doesn't matter if it's even or odd, because we only know f of x on one side anyway. We only know it from 0 to L. Which means, this says theoretically you would extend it as an odd function. The solution is always the solution you get by extending it as an odd function and finding a Fourier series. Now, at this point, some of the quacks are going to start talking about, oh, math is so beautiful, isn't that so beautiful how this all works out? And it seems like really, like, that's convenient until you learn the history and you know that Fourier invented the Fourier series to solve the heat equation.
oh wow, okay.
So it's not a coincidence. Fourier literally went through the same path that we went through, ended up here, and then is like, how do I solve this? Then he went and constructed a whole other series of saying, okay, let's pretend I have a series of sines and cosines, let's figure out what these guys gotta look like. He invented the Fourier series because he wanted to solve the heat equation. He was actually studying the heat equation when he came up with Fourier series. The Fourier series was a means to an end. So the fact that this is not a coincidence at all either. So it's not like, oh, it's a Fourier series. No, Fourier was the guy who was solving the heat equation. He was the guy who solved it in 1800. He was the guy studying heat.
So the Fourier series itself is a consequence of him trying to figure out.
Right, he's trying to figure out this problem and he had to invent something to solve the problem. He invented the Fourier series. Right? That's how you know you're a badass. Right? When you can just like, this math problem is tough. I'll invent some math, put my name on it, and just like, that's the solution, guys. So, it turns out that that means we actually know how to solve the heat equation, which is a boundary value problem. So, at the end of the day, the problem is going to look scary, but the solution is going to be super easy. So, here's what we know. Given this problem, so t equals alpha squared uxx, you're also told that u of 0t equals u of lt equals 0 for all t greater than 0, and you're given that u of x0 equals f of x for all x between 0 and L. Given this, where of course this is your thermal diffusivity constant, which will depend on the material that you're looking at, because it will depend on its specific heat, its density, its heat conduction capabilities. So given that situation, the solution is given by. And from now on, you don't derive this, you just know this is the solution, this is the answer. U of xt is going to be given by the series e to the minus n squared pi squared alpha squared t over L squared times sine of n pi x over L, where your Cn is 2 over L integrated from 0 to L of x sine n pi x over L. That's how to solve the heat. Now, what we often do in finals, which is what I'm going to cheat and do right now, is usually they give you a problem and they say, hey, find the Fourier sine series. And then in part B, they're going to throw a heat equation at you. Oh, let f of x be the function in part A, assuming that a rod has these properties and that gives you the initial temperature distribution, solve this PDE that gives the temperature at any position x and time t in the future. And literally all you're going to do is take your answer from the Fourier series part and put it there, and you're done.
Wow, really?
Yeah, so that's it. So let's actually look at a problem like that. So let's steal one that we did last time. So last time, so let's take an example. Last time, we found the sine series for f of x equals x times 1 minus x, I believe. Did we do that? Right? So we have a function that looks like this, between 0 and L. Well, it was between 0 and 1, but our 1 ended up being L, which kind of looks like the situation I had before, right? Something is heating up in the middle. And then it's kind of that temperature distribution in this material is bulging like that. So at the ends it cools down all the way down to 0, but in the middle it's very hot, right? So what was the answer to this one?
Find A naught first.
I thought we only did the sine series.
Yeah, we
Yeah,
only do
we
sine
only do
series.
Oh, okay.
Yeah, so we didn't need the A's at all. We only
It was
found the B's.
Oh, right.
it was a long one. It's from 0 to infinity, k is equal to 0. Or you
N
can
is
do
odd.
odd, n is odd or k is 0.
Okay. But just give me the n odd version. Yeah.
H over n cubed pi q. Sine pi x n.
Sine.
Pi x n. There's no.
Because L was 1.
Yeah.
in that. Right. Which means the coefficient was this guy, right?
Yeah.
This was the Bn. Right? That was how we find the Fourier coefficient.
Yeah.
Okay, so now, follow up, bonus. Consider the boundary value problem. Ut equals 16uxx. So there's some material where the thermal diffusivity is 16 at position 0 and at position 1. This function measures 0, and u of x0 is f of x, which is x times 1 minus x. This will work for all x between 0 and 1. This will work for all t greater than 0. So you can consider this problem, and they might even tell you, oh, we have some material that we're conducting heat through, and this is the PDE that came as a result. Our initial conditions look like this, our boundary conditions look like that. It happens to be given by the function that you found the Fourier sine series for in the beginning. Solve. Now, if you're absent from class, it's going to be very hard to do, but if you show it up, the solution is literally going to be this. You are going to say, then, I mean, sometimes just to be nice, I actually write out so here's would be my answer to part B of this question. U would be n-1 to infinity Cn minus n squared pi squared alpha squared t over L squared sine n pi x over L where L equals 1, alpha squared equals 16, and your Cn is given by 2 over 1, integral from 0 to 1, of x times 1 minus x sine n by x dx, which was computed above. So you kind of set it out. Here's what the answer is going to look like. It's going to have this form. My L is 1, my alpha squared is 16 because it shows up in the position of alpha squared in that formula that you memorized. And we actually made this computation before. I know that the Cn will be given by the Fourier sine series coefficient, and the previous question asked me to compute the Fourier sine series coefficient. So there's actually no new computation to be made. I just now need to plug in my answer.
How'd you get alpha squared 16?
Because it's always ut equals alpha squared uxx. So the number in front of this, the number in front of the uxx is always alpha squared.
Yeah, but how is it 16?
It's just a given.
Oh, it was given?
Yes, it's literally just given. So that, the problem would give you that,
Okay.
right? And so then you say the solution is therefore given by u of xt equals the series over all odd n of 8 over n cubed pi cubed e to the minus n squared pi squared 16t sine of n pi x. That's it. So the hard part to this question is actually computing the Fourier coefficient, but you would have done that in another part. Or if there is a problem where it's not a follow-up, that's all you would do. You would write out that that's what the answer should look like and just compute this integral on the spot, and then just plug in the answer right there. But that's it. That's all there is.
It's a lot to memorize.
So in this case, we solve C.
Yeah, that's the hard part about this. Like that's not given to you. So the Laplace table is going to be given to you, but that's not going to be given to you. So this is just something you have to remember.
Oh, so Cn is equal to 8 over n cubed pi.
Yeah, the Cn is exactly the Dn from the Fourier series formula.
We're going to maintain the convention that on the outside of the integral is going to be 2 over L, right?
Yeah, because we're doing the half. Because this is odd and that is odd. So multiplying them together makes an even function. So we can double the answer on half the window.
Okay, I see.
Same as being
I see
from
why we did that.
Fourier sine series.
So if you give us an easier integral by reducing it, it should just be twice that, because that area
Yeah.
will be twice that.
I mean, you could do 1 over L from minus 1 to 1, you'd get the same answer.
Yeah, I think on one of the old tests, they used a different convention for that and just did the full integral.
Yeah, I don't know. If you're finding a sine series, or you know your f is odd, you only have to do half. The only way you have to do the whole integral is if your function isn't odd, or it isn't even, it's neither. So, if you had if your f of x was x cubed plus 1, then you'd have to do the whole thing.
Yeah, because you wouldn't be able to deduce that it would just be twice that, right?
Right.
So
Or if they told you f of x was x cubed plus 1, but they happen to put it here, what you do is you cut off half of it and you just extend it as an odd function. So while x cubed plus 1 by itself isn't odd, because it would look like that, if someone gave you that, what you would do is you ignore this part and then pretend that it looks like this. Right? You kind of just extend it as an odd function. So you slice off half of it, you don't care about it. Yeah.
So Cn here is equal to a over n cubed pi cubed.
Cn is equal to what?
A over n cubed pi cubed. The blue circle.
yeah.
Yeah, Cn is same as Bn.
Cn is the same as Bn from the Fourier sine series,
Which is 8.
Yeah, okay.
which is 8 over n cubed pi cubed. Because we found that last time.
So is this gonna be like on the test or is it a bonus question?
This is a bonus, but
It's gonna be on the
for what it's worth, it's an easy bonus. Because I'm going to ask you to compute a Fourier series in the test. So you're just gonna copy your answer from there to this location.
Oh, you're gonna give us the CN, whatever?
I'm not gonna give you this, you're gonna find the CN. I'm gonna have you find the
You
CN
said it was easy.
in the test. Like some of the heat equation is easy.
Like,
Like,
you get the wrong CN, but you do that part right, you're gonna give us a bonus?
Yeah.
Oh, okay. Touche.
so you, yeah, so you find the Fourier sine series. Let's say you get that wrong, but then in part B there's a follow-up to solve a heat equation based on the original function. Then yeah, if you plug that, whatever you got here, you'll get full credit for that part. Yeah.
Alright.
Because it's just a matter of you knowing what the formula is and what position to plug everything into. So you are normally going to plug in your alpha squared because that will be a number that you can get from the problem. You're going to plug in the L because they'll tell you the interval, they'll tell you the length of the bar, or they'll tell you what interval you're working on. And then the Cn is just a Fourier sine series, which you may have computed previously, so you can just do that. So pretty much what I wrote here in the box originally is what you need to remember that what the formula looks like and what the solution looks like. And then it's just a matter of plugging in.
Pi squared, alpha squared, e to that, C1 times
And that's the heat equation.
Sorry, what is it from the form that we would need to know?
Huh?
What is it in the form right here that we would need to know to solve this?
You need to know the whole form. So you need to know that a problem can be given to you that's going to have this form. Where the L is going to be a specific number. It's going to be the length of the bar or half the interval of consideration. And we're going to tell you that at time 0, this is given by some function, right? So you just seeing that written on a piece of paper, you automatically know what the answer looks like. The solution will look like u of xt. Where whatever number showed up here, you're going to put that number here and here. And then whatever number shows up in front of the uxx, you're going to put that number here. And then to compute the c's, whatever number was here, you're going to put that in the denominator, and in the limits of the integral, you're going to integrate the function times sine n pi x over that. Okay. You find that answer, you're going to plug it in here, and you're going to box that.
So the left-hand side, that will be given like that?
So this is given, that's how the problem's going to be given. It's like me giving you a differential equation and say solve it, right? So I'm going to give this to you, I'm going to say solve it, and you're supposed to know, oh, that's what the answer looks like, here's how I compute this here.
Does this only have to do with the rods?
No, it more generally, it is what's called the diffusion equation. It's just that it was invented by considering heat conduction. But it turns out that a lot of things would actually behave this way. The way that gas would diffuse in a room, the way that pollution would diffuse in the atmosphere. It turns out this can measure a lot of things that diffuse. Heat actually diffuses quite familiarly with other
Didn't
things.
he hypothesize like the greenhouse gas effect in like the 1800s or something like that?
Yeah, yeah. So you can predict some crazy things with this. Yeah. So like I said, the wave equation, these are the fundamental ones, the wave equation, the Laplace equation, the heat equation. Heat equation covers diffusions of all kinds. Like they can be covered by this PDEs. It's crazy. The wave equation, so once you're studying fluids, like you just want to know how waves behave, if you're studying fluids or sounds or anything like that, you use the wave equation all the time. If you're studying deformation of bodies, gravitation, you use the Laplace equation all the time. So they're fundamental examples. But for us in 391, we're always going to either consider it as a heat equation or just some unknown system that you need to solve, where we're going to ask you to actually compute the answer in some previous part. You just need to know what to do with it. Yeah.
So just to double check for the test, when we have the litmus test for like, you ask us a sine series, for instance, right? We're gonna automatically assume that an is equal to 0
Right,
and just go for it.
just find Bn.
Find Bn and then put Bn into a nice series form where we decide if it's odd or, I mean, I guess for Bn it would always be if n odd.
You would always be odd, yeah.
So if we
So
have.
you're always just going to say Bn is 2 over L, 0 to L of the function times sine.
Okay, and then the opposite is true for cosine at least.
Yeah, if it's a cosine series, you'd have to find the A0 and the An and ignore the Bn.
Okay.
In every other case, you have to find both of them.
Okay, so cosine is unique in that you have to find both A naught and
An, yeah.
Okay.
Find all the A's for cosine, find the B's for sine. You find both for all other situations.
And the second question was for the general find the Fourier series, the following function one. We're finding all of them for that one, right?
Yeah, A0, A, and B.
And would you recommend drawing a picture for that, like so that we can better visualize the period and stuff, or should I just kind of
I would probably draw it.
draw
Because
it?
usually the function isn't going to be complicated.
Okay.
Because, I mean, you're throwing it in this kind of integral, like it's,
Yeah, it's.
we don't want it to take forever.
You're just kind of.
So
putting it-
it's going to be like a constant or some polynomial which shouldn't be larger than a quadratic. So it's not going to be something crazy. So I'd actually sketch it, because if you sketch it and you realize that it's an odd function, even though the problem doesn't tell you it's odd, you would actually just ignore all the ANs. You would know to not do them
Okay.
ahead of time. Yeah.
So you could reach the same kind of situation
Yeah.
based off of whatever the function was. where
Yeah,
something
so
was-
when it comes to Fourier series, there are 3 situations. I can just give you a function, not give you any information, just say find the Fourier series. Or I can specify, find the cosine series, or find the sine series.
And it could be any 3 of those, right?
And it can be any 3 of those. However, when I give you a heat equation, I say, okay, this PDE describes the heat conduction in a rod, solve it. It is always the sine series coefficient.
Ah,
You
okay.
always use the Bn in all situations.
So
it's always going to be
If
a
there
Bn.
were to be this kind of problem, we would need a sine series.
You would need a sine series. So you would have to make sure. So let's say I gave you a previous problem where I asked you just find the general series, right? So you find the A0, the A, and the Bn. And then I give you this with the same formula. You should know that you're going to look at the Bn part of that problem, ignore everything else.
Okay.
You just want the Bn part of that problem and put it here.
Then I got you on tape saying it.
Yes. That's the way to do it. That's the right answer.
No, so I can go back and listen to it again.
Yeah, so you can go back and you just know. If you're solving a heat equation, it's the sine series. It's always the sine series.
Gotcha.
Because it comes from us solving that equation, y double prime plus lambda y equals 0. It gave us a sine as the answer. The only non-trivial case was a sine. It's always going to be the sine. There are other cases where it's always a cosine, but that's not in our syllabus.
I gotcha. Anybody else have questions about the test?
So if you're saying that they're related, then that means you're guaranteed to give us a sine series then?
No, like I said, I could give you a general one, but you know if you're doing this part of the problem, you only look at the Bn part of the general. You ignore the An parts.
Can you go to roots of unity without using 1 as the coefficient?
Without using one.
1 as a coefficient. So it's like r squared plus 5y. I mean, yeah, r squared plus 5 or something.
Yeah, those aren't actually too different. Those are because you just take the radical. So if you have a
No, using roots of unity.
yeah. So if you have r cubed plus 5 equals 0, right? You want to find all the complex roots of that. Well, if you move that to the other side, you get minus 5. And what you would do is you think of this as 5 times minus 1. Right? So the minus 1 is what you're going to rewrite in the exponentials.
Okay.
Right? So this is e to the I pi, right? Plus 2n pi. So this looks like this would look like 2n plus 1 pi equals r2. And so your r then would just be take the cube root of both sides. So it's the cube root of 5 times e to the 2n plus 1 pi over 3. Now this is just a constant. You just leave it alone. Just leave it in position while you compute these things.
Okay.
So, and then you just let n equals 0, 1, and 2.
test, are you gonna specify, which, kind of series to use for such a thing, or like for different things? Because,
Or,
I know that depending on if,
so here, n equals 0, let's just finish this up. N equals 0, you get e to the pi, e to the I, pi over 3, and that would be what? So you have, your R1 is cube root of 5
times
cosine pi over 3 plus I
sine pi over 3,
cube root of 5 sine pi over 3.
cosine pi over 3
Cosine pi over 3
Half,
is,
half sine of pi over 3
square root 3 over 3.
radical 3 over 2.
you're on that case, the unit circle.
R2, you would have the cube root of 5. This means you plug in, say, n equals 1. So that's e to the I pi, which is minus 1. So that means automatically your R3 is just going to be this with a negative sign here.
It's just harkening back to the quadratic formula, right?
That's that. So the 3 roots is this, and plus or minus that. So if you were doing this as, say, a homogeneous solution to y triple prime plus 5y equals 0, then your homogeneous solution would look like C1 e to the minus radical the cube root of 5t plus C2 e to the cube root of 5 over t e to the t times cosine of this guy times t plus that times sine of that guy times t. Yeah, so if there's a number other than 1, you just factor it off. Like you,
Oh, so let's
you
say it
just
was
keep
like
it.
r to the 7 plus 87. So for r equal, it would be like 7th root of.
So if this was 7 and that was 87,
Yeah. You
then
would just replace
this is going to be
7.
7, that's going to be 87,
And
and
three.
that's going to be 7.
And you would do n up to all the way 0 to 6.
To 6, yes.
Okay.
So then 3, 4, 5, 6.
And you just keep on going, and you just add every single one of them up.
Yeah, you add them all up, you get 7 linearly independent.
But you need to solve for them.
So on certain problems, it'll say like, just find a regular power series. And then on other problems, it'll kind of imply that you have to use the Frobenius series to do it. Will we have to choose which series to use, or will it kind of be, you know, because I know you can test the singular points, and if you have x equals 0 as a singular point, then
Yeah, like in general, you should be checking on your own, but I'm gonna like tell you when there's a single point for you to consider.
yeah, I've gotten good at knowing, but it takes me a few minutes to like feel like, all right, this is the right one.
Because normally what it'll always tell you, we want the power series solution centered here. Now you should be able to recognize if that center is actually a singular point or not,
Yeah.
right? Just by me telling you, oh, you realize, oh, that actually makes the coefficient 0 here, which is going to create a singular point. So you would know, but the problems always kind of tell you about the singular point first. Show that this is a regular singular point. Now find the series solution. Like I'm going to kind of be the
I
same.
gotcha. And just so that I get it in my head once and for all, if x equals 0 is a singular point, then that means that we can use the Frobenius method?
If you want a series solution at 0, then yes, you have to use the Frobenius method with n plus r in the power.
Okay.
Assuming that it's a regular singular point.
Is it okay to put that r in at the beginning? Because I know we can solve for it
You mean if
using
you find the value from the beginning?
Yeah, so we can solve for the r using Euler's equation, and then plug it in right at the start.
Yeah, so if I like ask you, find the solution corresponding to the larger root,
We would have
then
to
in
find it.
theory, then yes, you can plug it in from the beginning, but it's okay to do it at the end.
Okay, because I guess because sometimes you get like a half or something, so.
Yeah, like
Oh,
you
yeah,
don't want
better.
to copy down a half.
Yeah.
Copy down r is probably nicer. You just plug in the r at the end. Just before you start computing the coefficients, plug in the r at that point.
Okay, thank you.
Other questions?
We know all the differential equations.
So that's the heat equation, pretty cool, but the solution is actually easy. And
How much of partial differential equations do you know?
that's all you have to know
No,
about.
like, calculus class, how much do we know out of like all partial differential equations?
Huh?
On a scale of 1 to 10, how much of partial differential equations do we know right now?
Oh, differential equations in general, not many of them are, like, they're hard in general. But, yeah. So we're a little bit over time, but I think we have to do this. You have to tell the world how much you love these. We need a volunteer to collect these surveys. So we'll do that, and then you guys can all leave. You're looking at this one? Yeah, there's a code I have to write down for this.
Professor, can you post the mock solutions?
Okay, so do I have a volunteer who's going to collect all this stuff?
I'll do it. I'm careful.
Not Omer. Omer has to go on a boat. So. How do you know that? So someone pass it to him first. Let him get out of here.
Whoa, no. Have you listening to me or something?
Just pass it.
I appreciate it, bro. Thank you.
So I guess that's you, Chris. You're the volunteer.
I can't walk. But I'll do it anyway.
Just pass it back. Excuse me. Get this here.